It hasn't been that long that we've actually talked about weather and climate in the same conversation. Scientists are just now starting to make these connections between what's happening in the climate system and how it's affecting our weather patterns. I think we can all agree that Mother Nature in the last several years has dished up an incredible smorgasbord of extreme weather. And we've seen just all sorts of types of extreme weather coming up. And so what I want to do today is bring you up to date on some recent research that's connecting climate change with extreme weather events, and tell you the bottom line first, and that is the evidence is really starting to pile up. So I don't know about you, but I've been noticing a real change in the conversation that I've been hearing in the public, in interviews with media, with journalists, on TV. People are really starting to notice that extreme weather is increasing. It's affecting everybody personally, not just here in the United States, and they're starting to ask questions. What the heck is going on? Is this climate change? Some of the things we've heard just in the last year very frequently, the word unprecedented. We seem to be hearing that word all the time in connection with weather. Global weirding, that was a new one that came up this year. Weather madness, hell and high waters. We know what comes to mind with that one. And a new state. But I think maybe Mayor Bloomberg summed it up the best when he came out with this statement right after Sandy hit his backyard. And I know he was talking about more than just Sandy when he said this, and maybe he overstated just a little, but I think it got people's attention. So what I thought I'd start with is kind of a visual tour of some of the extreme weather that's happened in the last year or two, not just in the United States, which we've heard about already from Chris and some other people this week, but really around the whole northern hemisphere. It's just been darn weird. So for example, last summer, Venice, Italy, experienced some of the worst flooding it's ever had. That's saying something for Venice because they get a lot of floods there. The UK had some terrible flooding, followed right on the heels of some very bad drought conditions. China, just last summer, again, some very bad floods, a flood of floods. Vermont, 2 summers ago, when Irene hit them, they're still trying to recover from the damage from when Irene came through there. Last summer, Alaska was inundated with rainstorm after rainstorm, especially southeast Alaska. And even Greenland last summer, they had a lot of damage from melting ice, and even some rain washed out bridges. It did a lot of damage in Greenland. You don't normally hear about that. So in addition to flooding, we've also had a blizzard of cold and snow. Europe last winter had one of its worst winters ever. The cold and snow extended all the way down to the south shores of the Mediterranean Sea. China, just this past month, and Russia had some of the worst cold temperatures they've experienced in a generation. Last winter, Alaska, southeast Alaska, had the most snow they've ever had. And that's saying something for Alaska because they get a whole lot of snow. You can see these fishing boats just buried in snow. And I love this picture. I hope you can see it in the back there because it's a road up in southeast Alaska, and there's a little car down there. And I would love to see the snowplow that managed to dig that gap. I mean, it's just hard to imagine. And then over in Russia, they also had some pretty bad snow, and some of their local residents were having a hard time dealing with it. So then, of course, there's the other flavor, heat, drought, and fires, which of course was such a huge story in our country, where we had heat waves all across most of the Midwest this past summer, with its attendant drought. Texas was particularly hard hit. Some of its marinas completely dried up. The fires in Alaska were very bad this summer and all across the western part of the country. And the heat was bad in other places too. This picture probably doesn't look all that unusual to you until you take into account that this was last March in Burlington, Vermont. Russia, for the last few summers, has experienced some extreme drought and heat waves as well. As I mentioned, Europe had drought followed by flooding. And even here last winter, people were crying about the snow drought. So there's all kinds of droughts. And then, of course, we've heard a lot about Sandy already this week. And some of the pictures that came out of this storm we'll never forget. They're etched in our minds. It was just an incredible event. And, of course, the questions about what role climate change played in this storm continue to come. And even the fact that it was a major snowstorm as well. So let me just follow that up. If that doesn't hit home, here's a few more sobering facts that I think Ground, and now the Weather Company too, said recently. During the last 7 years, we've broken pretty much every kind of weather record there is, from heat to tornadoes to floods. And here's some examples of that. 2012, we just found out, was the warmest and second most extreme year in U.S. history. This past March was the warmest March in U.S. history. This past whole spring, the most extreme season in U.S. history. This past June broke or tied 3,215 high temperature records in the U.S. alone. July 2012, this past July, was the hottest month in U.S. history. September 2012, Earth's warmest September on record for the whole Earth. November 2012, Earth's 333rd consecutive warmer than average month. And then last spring, in 2011, was the most extreme on record for precipitation in the U.S., and clearly we just saw 2010 was really bad too. July 2011 was the most extreme July on record for the U.S. I mean, the list is just mind-boggling. And then finally, 10 of the 11 warmest years on record worldwide observed since 1998. So what the heck is going on here? And really, the question is becoming, is human-caused climate change playing a role? And I think for many years, up until very recently, scientists were very hesitant to weigh in on this topic. But more and more we're hearing that it's not something that people are shying away from anymore. And I'm one of those. And I think climate change is playing a very huge role. And that's what I want to talk about today. So first I want to put it into perspective. Here, you've probably seen a graph like this many times over your career. But what we're looking at here is going back about 450,000 years into the past and looking at how temperature and carbon dioxide in the atmosphere have been changing over time. And you can see that there's a very clear relationship between the two. Generally, when carbon dioxide is high, which is the blue line there, temperature is also high. But what I want you to focus on here is over near present time here, where the CO2 has shot up to levels that we haven't seen in at least 650,000 years. And what you should also notice is that the temperature has not yet responded. It takes a long time for the Earth to come into new equilibrium with this new concentration of carbon dioxide in the atmosphere. So what this means is that we have, just because of the carbon dioxide that's already in the atmosphere, we have a long way to go in terms of warming and the impacts of this high carbon dioxide in the atmosphere. And we know that the reason the carbon dioxide is so high now is because humans have put it there. And it's not slowing down. So more recently then, we've started to see some of the impacts of this higher carbon dioxide in the atmosphere. In terms of global temperatures, this goes back to about 1880 from NOAA, where these are the global temperature anomalies up to present day, and you see that there's a very clear trend upward in the global temperatures. And they are not evenly distributed around the globe, as you can see from this plot of temperature anomalies just for the last decade from NASA. And you can see that while there are warm colors pretty much everywhere on the globe, the high northern latitudes are where the warming is happening the fastest and the largest. How do we know that humans are to blame for what we're observing? So let me just give an example of one of the tools that we have that helps us know for sure that humans are really causing this temperature rise. And one of our best tools for doing this are these computer programs that we call global climate models. They're very complicated computer programs based on math and physics, and what they try to do is simulate all the processes that happen in the climate system, in the atmosphere, in the ocean, in the snow and the ice and the land surface, and all of these processes acting and interacting with each other, and then how the forces acting upon them are going to make them change. So what we can do is we can run these models with and without greenhouse gas increases in them. Oops. And so here's an example of one of these comparisons here. So what you see is the black curve here is the global average temperature starting at the beginning of 1900 or so, and how it's evolved over time. You can see that it wiggles up and down somewhat. And the blue line here is the model, the climate model simulation, but only including changes in what the sun output has been doing, in volcanic eruptions, and natural changes in the climate system. So what you can see is that the two agree pretty well. The models are pretty good at capturing what the real world did up until about 1960. But then after 1960, what we see is that the two separate from each other. The model thinks that even though there's been these volcanic eruptions, which are those vertical lines there, that the temperature should have been gradually decreasing over time, reflecting the natural changes in the climate system and the natural forcings on the climate system. But what the real world did was something completely different, and that was this increasing global temperature in the last several decades. So now what we can do is tell these same models that in fact the greenhouse gases in the atmosphere have increased a lot during this period. And if we do that, then we get a much better agreement. The model run is now in red. The observations again is the black line, and we see that the two agree quite well. So this is a very important clue telling us that without telling the models about greenhouse gas increases, there's no way that the models are going to be able to simulate what's happened in the last few decades. And so this is just one of the ways that we can tell for sure that human-caused climate change is having this impact on global temperatures. So not only is the temperature increasing, which itself is an addition of energy to the climate system, but also the atmosphere is gaining moisture. And we can see this going back to about 1970. There's been a very steady increase in the amount of moisture in the global atmosphere, about 5% in the last several decades. And as you know, moisture or latent heat is fuel for storms, and the extra moisture in the atmosphere also provides more moisture for precipitation and heavy precipitation events and things like that. We also know that the effects of that extra water vapor in the atmosphere are not uniformly felt around the globe. And these two plots here, which you probably can't see very well, but you really just need to see the colors, are the December or the winter and the summer projections of what precipitation changes are going to happen by the end of the century by these climate models. And basically what you see is that the high latitudes, which tend to be wet anyway, are going to get even wetter. And the dry areas, because of the atmosphere warming, evaporation is going to increase. Those dry areas are going to get even drier. So there's going to be more extremes in precipitation in both directions. So this means between temperature and moisture, we have changed the deck of cards that we're playing with in terms of the climate system. So I've got my little deck of cards here that I brought along, just a normal deck of cards. And to illustrate this change that's happened, what I'm going to do is I'm going to take out a couple of low cards, say the 3 of clubs and the 2 of diamonds. We're going to get rid of those. And instead, I'm going to add an extra King of Hearts, which of course is the king with a knife through its head, and the Ace of Spades. So we've got an extra king and ace in the deck now. And this is the deck that Mother Nature is playing with now. So if she goes and deals a hand of poker, then the chances of getting high cards is going to be much higher. But that doesn't mean that every hand is going to be a good hand. So it's another analogy for showing how this change in the climate system is increasing the probability of getting extreme events. So now I want to focus more in on the Arctic, which is where my heart lies, sort of, research-wise anyway. And what we're looking at here are the temperature changes over the last decade or so over the whole northern hemisphere. And once again, what you see is that there's been general warming. Anything that's in the greens and yellows is warmer than climatology. And you can see up in the far north is where the warming has been the largest. In fact, the Arctic has warmed at least twice as fast as the rest of the northern hemisphere. And when we can look at this by latitude zone as well. So what we're seeing here is how the temperature has changed in various latitude zones since the late 1950s or so. The light blue line here is the one for the Arctic. And you can clearly see that the warming in the Arctic has been accelerating, especially in the last couple of decades. And also interesting here is the green line, which is for the northern mid-latitude zones, so where we are right now. And interestingly, it is warming for sure, but that warming has leveled off in the last couple decades. And so what that means is this gap between the Arctic and the mid-latitudes has been increasing. And this is what we know as Arctic amplification. We can also look at how the Arctic warming has been changing by season and through height in the atmosphere. So these plots are showing temperature trends for winter, spring, summer, and fall from 40 degrees north up to the North Pole, and also on the vertical axis is height. So what you notice is that the warming trends or the temperature trends are largest in the winter and in the fall, but they also happen in the spring and the summer. It warms in all seasons. The warming tends to be largest down by the surface, but it does extend all the way up to the top of the troposphere. So this is a very large signal that we're seeing. And I'd like to mention, if you think back to that plot I showed you of CO2 and temperature over the last several 100,000 years, the last time the Arctic was as warm as it is now, which was about 125,000 years ago, the sea level was 6 to 8 meters higher. And this goes back to what I said earlier about how the Earth hasn't caught up yet with the carbon dioxide levels that we have in the atmosphere right now. This is really bad news. And speaking of bad news, 2012 was just a horrible year for the Arctic. Here's one example. This is the amount of snow cover during the spring over the whole northern hemisphere land areas, and how it's changed over time starting around the mid-1960s. So this is the amount of snow cover in terms of anomalies going back to the 1960s up to present. And what you can see is that starting around about 1990 or so, these anomalies in the snow cover just started to go through the basement. And in fact, this past summer, we just totally obliterated the record in both June and July for the minimum amount of snow on high latitude land. Greenland is another big story this summer. For the first time in at least 150 years, the entire surface of Greenland melted for a few days, about 98% of the surface. And then, of course, the sea ice was also a huge story this year. And now I would call it a mere shadow of its former self. Its former self looks like this. Looking down with a satellite on the North Pole, you can see Greenland there. This pink stuff is all of the sea ice that it used to look like this back in only 1980 at the end of the summer. So this is the time when the ice is at its minimum extent. But this summer, it looked like this. And you can see that it's much, much smaller than it was only since 1980. And in fact, the amount of ice has decreased in area by about half in only 30 years. So then if you take into account the thickness of the ice, and you multiply the thickness times the area, you get the volume. The volume is now 80% less than it was only 30 years ago. And what's left now in the summer, you can see the colors look a little different from what they used to look like back in 1980. That means that the ice that's left is very broken, it's very thin, it's rotten, it's slushy, and that means that any anomalies in the winds or heating events or whatever that come along can easily melt that ice. It's a very vulnerable ice cover now. Well, you might be wondering, has this happened before? Is this really unusual for the ice to be this small? Well, if we go back in time, and we can do that pretty well to say the end of the 1880s or so, because there were whaling ships up there, and there were quite a few people working the edge of the ice, and so we have reasonable records going back that far. And what we can see is that during the summer ice extent, it up until about 1950 or so, it wiggled around a little bit, but it was very steady actually. But then starting around 1950 or so, things really started to change. And the ice cover, the extent of the ice, really started to drop off. And just in the last couple of decades, we've seen an acceleration in the ice loss. And if we put 2012 on this chart, you can see that we're in just all new territory. We can look back even farther in time, actually. This was a new study that came out by Kennard et al. Last year using sediment cores in the Arctic Ocean and looking at the kinds of little critters that settled in the mud down at the bottom of the Arctic Ocean. And those kinds of critters vary depending on whether there was ice on the surface or whether the surface was open water. And by using that information, he could go back almost 1,500 years and estimate how much ice there was at the end of the summer covering the Arctic Ocean, and that's what this graph shows here. And what you can see is that, there's a lot of wiggles from year to year and some uncertainty, but overall it was relatively steady. And particularly if you take into account this blue line here, which is the more modern record, and how it's dropped off so much just in the last several decades. And again, if I put 2012 on here, we're in uncharted territory. So I mentioned that not only is the ice getting smaller in extent, but it's also getting much, much thinner. And what this little animation shows is through the whole season, not just summer now, but all the way from January right through December, and go looking through time, how the thickness of the ice, this is actually the volume of the ice, how it's been changing from year to year in all of the months of the year. And you can see that it's a very steady decline in every season, year by year, and right up to where we are now, or almost now. This goes through almost to the end of summer 2012. So if we consider a layer of atmosphere, say the bottom 500 millibars, stretching from, say, Colorado up to the Arctic, and this is illustrated here by the top of this layer, from Colorado here, where it's much warmer, of course, up to the Arctic. And we know that warmer air takes up more vertical space than colder air. So this leaves us with this slope, this surface of the top of this layer of atmosphere that has a hill. And what the air tends to do is it wants to flow downhill towards the Arctic. And because the Earth is spinning, the Coriolis force sends that moving air that's trying to flow north to the right, and we end up with the jet stream, this river of fast-moving air at high levels over our heads. But as we warm the Arctic more than we warm the mid-latitudes, this layer of air becomes, the hill that it creates is less steep. And so this causes the jet stream to weaken in the zonal direction. So the west to east winds of the jet stream should weaken because of this Arctic amplification. So the result, that's the first effect that we expect to see as a result of Arctic amplification. And in fact, if we look at observations, if we look at the NCEP reanalysis for what the 500 millibar zonal winds have been doing over the last several decades, going back to 1980, right up to present, what we see here is in the fall now, this black line is the actual observed zonal wind at 500 millibars, and you can see that very clearly it has been decreasing. And in fact, its speeds are about 10% lower than they were, say, back around 1990. We also noticed that they really started to drop off right when the sea ice really started to disappear. And the dotted line here is the sea ice area at the end of summer. And what you can see is that right as the ice started to drop off, that's about when the zonal wind started to decrease too. So this is what we expect to happen. This is what we're seeing happening. When the jet stream winds get weaker in the zonal direction, through Rossby theory, we know that a weaker jet stream, and just through your own experience as meteorologists, you know that when the jet stream is kind of weak and sluggish, it tends to meander more. You see it on your weather maps. And we also know that when it has this more meandering trajectory, the waves that we see in the jet stream, especially the large-scale waves, tend to not move very fast. So that's the first effect. The second effect that we hypothesized was this idea that if you take a contour of the 500 millibar height field, say this wave, typical Rossby wave or large-scale wave over North America here, and you warm, because of Arctic amplification, if we warm the northern part of this wave more than the southern part of this wave, then the 500 millibar heights in the ridges are going to increase more than they are in the troughs. So that means if you want to stay on this, say you're walking along this height contour, and you want to stay on that height contour, you're actually going to have to go farther north to be at that same height. So the effect of this is that the waves, the large-scale waves in the flow, are actually getting stretched in the north-south direction. This is another factor that's causing the flow to become more meandering. This is a little animation of the actual jet stream. This is created with real data by NASA's Science Visualization Laboratory. And what you're seeing here are little vectors showing what the winds are doing at something like 500 millibars or so. The colors indicate the wind speed, so the red colors here are where the winds are faster. Right now we're looking down on the northern hemisphere, down on the North Pole, and what you can see is a typical sort of jet stream encircling the entire northern hemisphere. So as I put this in motion, what you're going to see is these waves in the jet stream that we're all familiar with. And there are times when these waves are relatively low amplitude, and we know that in this kind of a condition, the storms tend to ride pretty quickly across the northern hemisphere. So when I start this up again, what you're going to see is the character of this wave change over time. And it's going to go into this configuration now of being much higher amplitude. And as you'll notice, as I set it in motion again, these waves, these big, large-scale waves in the jet stream are not going to move very fast across the northern hemisphere. They tend to be kind of stuck. We tend to see cutoff lows. We tend to see blocking highs. And we tend to see a lot of messy stuff going on too. The jet stream is not a simple creature. So I just tossed this in here as sort of corroborating evidence, this paper that came out last year showing an estimate of, or a measure of the blocking index over Greenland, going back to the 1940s, the beginning of the NCEP reanalysis record. And you can see that it goes along quite steady, and then all of a sudden, around 1990 or so, just like so many of the other things I've shown you, it takes this big increasing turn, suggesting that the tendency for blocking over Greenland in the summer is increasing, and it's been observed. So it all is all hanging together. And I mentioned in the beginning that Greenland had a really bad year this past summer, and I think this tendency that we're seeing in the blocking over this part of the world is contributing to what we're seeing happening in Greenland. If we look back to 1992, not that long ago, when the surface of Greenland typically in the summer only melted where those orange areas are. So just a little tiny bit of the surface. The rest of it stays frozen. Only 10 years later, the amount of the surface that melted increased by a factor of, I don't know, must be like 5 or something like that in just one decade. A few years later, continued increase, and then again, here we see this past summer, the entire surface melting. So it wasn't just an unusual year this year, it's been this progression of increasing the amount of surface of Greenland that's been melting over time. So finally, what I thought I'd do is take some specific extreme weather events that are chosen particularly because they're the kind of events that are related to very persistent weather conditions, and see what the jet stream looked like when they happened. So let's take, for example, the record snows in Alaska last year, and see what the jet stream looked like during that time period. There's this really cool website that the San Francisco State University puts out where you can look at the jet stream pattern pretty much any day going back a long time. And you can do animations too. But this is showing what the jet stream pattern looked like during the time period when most of this snow fell back in January last year. And you can see here's Alaska up here, there's the coast of California, and you can see that the jet stream was in this highly amplified flow, a big trough in the Gulf of Alaska, bringing all this moisture right up into southeast Alaska where the snows were so heavy. And probably Matt is thinking, oh yeah, I remember when it was really dry in Oregon then too, because when you get a big trough, you usually have a big ridge right next to it. And so again, a very amplified flow during this extreme event. Last summer, or last September actually, just a few months ago, they had unprecedented flooding in Spain. And the jet stream pattern then, again, we're talking about a very highly amplified flow. Here's Spain right here, there's Greenland up there, so here's the northeast of North America. Again, a big ridge in the North Atlantic, big trough dipping down just west of Spain, bringing all this moisture right into Spain. And that was parked there for a good week. Whoop. So here's the March heat wave that we had just this past March with record-breaking temperatures over much of the east, and the jet stream pattern associated with that. Once again, big trough over the west with persistent low pressure, big ridge over the east, persistent high pressure, persistent being that key word. And finally, well, not quite finally, the past winter in Western Europe where they had snows all the way down to Morocco, and look at what the jet stream pattern looked like then. Big ridge sticking way up into the North Atlantic, big trough dipping down well south of Spain, bringing cold air well down into the Mediterranean. This was last February. So just last month they had this deadly freeze in Asia. There were dozens of people killed. Where we had these very low temperatures. These are the temperature anomalies over Asia, and that extended well over into Northern Europe and all the way down into China. And the jet stream pattern then, looking down on the whole northern hemisphere now, what we see is that here's Asia over here, and that doesn't look like a very highly amplified flow, but what's happening in the rest of the hemisphere certainly is. A big ridge over Alaska, and big trough and ridge situation down over Europe. So it's not allowing that jet stream over Asia to shift at all because the whole pattern is blocked up. And just this week, seeing we were talking about record temperatures in California, record low temperatures there, record high temperatures in the east, just looking at what the 500 millibar flow looked like, as Dale has mentioned in his briefings, this big ridge parked over the Pacific, big trough over the west coast, which we heard this morning is projected to stay there for a long time, and at least for another week. And again, we see this very, very highly amplified flow connected with a very slow-moving weather pattern, leading to the kinds of extreme weather that is associated with persistent weather patterns. So this is that slide that I mentioned about Sandy and the $64 billion question that I've been asked I don't know how many times, and whether Sandy was somehow connected to climate change and sea ice loss, because they happened so near each other in time. So I'm sure you've all seen a graphic like this one, where it shows the big trough that was in place over the Mississippi Valley, with the big blocking high stretching way up over Greenland. And of course, we know this big blocking high not only helped steer Sandy into the East Coast, but it also set up this huge area of very strong pressure gradient between Sandy and this big high, which created the large area all along the East Coast with those strong east winds just pounding the East Coast and bringing that huge storm surge in. So this very unusual situation that Sandy ran into as it came up from the south. What was the Arctic looking like at the same time? So here's the 850 millibar height anomalies for the week right before Sandy hit. Here's Greenland here, and you can see the big blocking high right over Greenland. And it extends well over the whole Arctic Ocean, undoubtedly connected with the loss of sea ice this past summer. So the question is whether this big block that was so important to Sandy's evolution was somehow strengthened or extended northward or prolonged by the Arctic amplification that was clearly in place at the time. And the warming like that I showed you here was extending all over the Arctic. Well, I think maybe it could have played a role. So as the ocean warms, the hurricane seasons may lengthen. So we might see more storms like Sandy forming later in the season. And the warming oceans may also allow these storms to move farther northward and track farther northward before they're weakened by the cold water, which is exactly what we saw was the case with Sandy. And perhaps, as John suggested, they're going to have more opportunities to interact with these very amplified flows that we expect to occur more often in the future. Maybe. So, in summary, I would say that our deck of cards has clearly changed. As I showed you, and I hope you'll remember that graph because I think it says a lot about the situation that we're in right now. The fact that the CO2 levels are higher than they've been in many, many thousands of years. We have a warmer world, we have a more moist atmosphere, and so any weather pattern that forms now is forming in a different state than it did only, say, 30, 40 years ago. We know that extreme weather of all types are increasing. We can see this in NOAA's Climate Extreme Index, and how going back to, say, the 1970s up to present, there's this definite increase in the frequency of extreme events in the U.S. We know many factors contribute to that. I think the Arctic may be one. Certainly the evidence is pointing to that. But Mother Nature will always throw us some curveballs, and we should be ready for those. So I think I presented a lot of evidence, and you've seen evidence for yourselves in your everyday jobs that extreme weather is increasing. And we're hearing more and more conversations and seeing more scientific studies that are connecting this enhanced and increased frequency of extreme weather and connecting it to what's happening in the climate system. But even with all that, we're still in this situation where the word is just not getting to the people who need to hear it and need to operate on that. But it's my hope that, as I said in my introductory video there, that we have an opportunity here because the public is listening now. I think they're realizing, they're seeing for themselves, they're being touched themselves by this extreme weather. They're seeing things like the ice disappearing, they're hearing about the snow disappearing, and they're not stupid, they are smart. And they're starting to question whether the misinformation that they've been hearing over all these years makes any sense at all. So I think we're starting to get a different conversation emerging out in the public there. And even if you don't believe it still somehow, the things that we need to do are just good anyway. And so, you know, I always try to end on an up note, and even though the science is pretty discouraging at times, but especially when I talk to young people, there's all these good reasons to make some changes, the kinds of changes that we need to do, not just for the climate system and the climate changes that we're observing in extreme weather as well, but for a whole host of other reasons. So thank you again for inviting me back. It's always a pleasure, and thank you for being such a great audience.